This is another application of the circulation version of the Green's theorem. You can actually start from a problem where you're trying to find the area of a region. You can write this as a double integral and try to rewrite it so it fits the formula of Green's theorem. In Green's theorem, the area of the region is supposed to be the difference of the partial derivatives of your vector value function. We're not given a vector value function, but we know there's supposed to be one here, so we can just rewrite it in a way so that we can make up a vector value function that meets the conditions. So I know that 1 is the same thing as 1 minus 0. I have many other ways of making number 1, but I just chose this way because it was simplest to my mind. After making that choice, that means my q partial derivative has to equal 1 and my p partial derivative has to equal 0. The next step is to go from the area or double integral to the line integral version over here. This time I take the integral of q partial x to get back to just q. I'm going to have a plus constant here and maybe a plus different constant right to this integral. As long as we can find appropriate values of q partial, p partial, subtracting each other to equal 1, the Green's theorem says the formulas are the same. So with multiple vector fields that meet the condition, you get the same answer. You might as well choose the easiest one with the zeros for constants. And notice by choosing p equal to 0, this piece of the integral disappears. I think it's always a good idea to graph your curve to see what this region looks like to get a sense of what you're actually integrating. GeoGebra is an excellent way to graph curves, and you can put this into GeoGebra by typing in the equation in coordinate form. I press enter, and it looks like it might be the curve, but I have to double check my interval. This wants me to go from 0 to just pi, and my interval that GeoGebra has is from 0 to 2 times pi. You can click on it, delete the 2, press enter, and now you have the appropriate region down here. I just want to get a sense of the orientation of my curve, so I chose a slide parameter that I can slide to say that, okay, is my curve oriented counterclockwise relative to my region, and I press play to see, oh yes, as I move my slide parameter on this particular curve, it's going in the right direction for counterclockwise. I forgot to substitute in this x into the correct place, but I've done it now. The next step is to substitute the components that we do know. X is given by the x coordinate in our curve, that's our path, which is why we wrote over here. The dy is given by the derivative of the y component and times the differential dt. I have x times dy, so that would be this particular integral is not so bad. A u substitution would work great on this interval. Set your u equal to cosine. Your du becomes a negative sign. Substitute your dt with the expression over here on the equal sign, and substitute your cosine with the expression over here. This is just a power rule then. Replace your u with the cosine and evaluate the limits of integration, which gives you 2/3 as your answer.